In this video, we will be learning about precipitation reactions and solubility rules. You'll want to have your green reference sheet handy so that you can look at the solubility rules. So what is a precipitation reaction? A precipitation reaction is when we start with two aqueous solutions and we end up with a solid. And so you can see these two aqueous solutions here. They have dissolved ions present in the solution. Following our double displacement reaction pattern, our cation will bond to an anion, cation bond to an anion, and if we have an insoluble substance form when that happens, then a solid will come out of solution. And so you can see the solid down here at the bottom is now solid down here at the bottom. There still are ions present in the solution, and that comes from soluble substances. So in this example, I'll be writing a complete ionic equation for this reaction. So in the first beaker, I had both potassium ions that are aqueous, and I have iodine atoms that are ions that are aqueous. And then in my second substance, I have lead ions, and I have nitrate ions. Following my double displacement reaction pattern, my lead from this beaker will want to bond with my iodine, and my potassium will want to bond with my nitrate. We will learn how to apply solubility rules shortly, but you can see here that I still have my potassium ions. Those are my potassium ions here, floating around in solution. And I still have my nitrate ions in solution. And then my insoluble solid is PbI2. Now, to balance this equation, I did need two iodines to make this compound neutral. And so I really needed two nitrates as well. I have to remember that these occur in a 1-to-1 ratio, so if I put a 2 coefficient in front of the iodine, it also needed to become in part of the potassium for balancing purposes. Since I ended up with 2 here, there will be 2 there. So the net ionic equation will involve my iodine and my lead. So how can you tell whether a substance will be soluble or not? So solubility refers to how much of a compound can dissolve in a given amount of solvent. So solubility is really a continuous scale. And so we're going to be classifying things as either insoluble or soluble, but I want you to realize that really it's not just black and white. There's a gray scale here. And so at some point we just have to say that so little dissolves that practically nothing dissolves. And so that would be insoluble. Soluble means a sizable amount it's able to be dissolved in solution. And so if it has low solubility, there are still ions present in solution. It's just not very many. You can see here the difference between barium sulfate and magnesium sulfate. Magnesium sulfate, you can dissolve 26 grams in 100 milliliters of water, compared to only 0.002 of a gram of barium sulfate. And so we describe barium sulfate as being insoluble and these compounds as being soluble. To determine whether an ionic compound is soluble or not, we will be referring to our solubility rules on your green sheet. So that's why I got this star here. This says refer to your green sheet. There are some patterns to help you remember these so that you don't have to rely on entirely upon your green sheet. So for instance, all of these are group 1. Group 1 and ammonium is going to be soluble. So if you have any of the group 1 metals or ammonium, it's going to be soluble no matter what. If you have nitrates or acetates, it's going to be soluble. Halogens and sulfates are generally soluble except for when paired with things that are pretty high charge. And so you can see a lot of these are high charge except for silver. Silver is only a +1. The rest are +2. And so it's just a pattern to help you remember. Additionally, silver, mercury, and lead, if you look on your green sheet, they're exceptions to a lot of things. Hydroxides, sulfides, carbonates, and phosphates are generally insoluble. So if you see something that's generally insoluble, your state of matter will be solid, except for when it's an exception to being insoluble, and then its state of matter will be aqueous. So if you see a hydroxide compound, then it's most likely going to be insoluble, unless it's a hydroxide paired with either group 1 or group 2. So here's some practice with solubility rules. Go ahead and pause the video and try to work out whether the compound is soluble or insoluble in solution. Unpause the video when you are ready to continue. Okay, so we want to find our anion for all of these. A lot of the solubility rules are based on the anion. So if we find hydroxide on there, it says hydroxides are generally insoluble except for those of group 1. Group 1, like potassium, are soluble. This is an exception to being insoluble, so it's soluble. And so my state of matter would be aqueous. Silver bromide. If I find bromine on here, bromides are generally soluble, except those containing silver. And so this one is insoluble. And so its state of matter will be solid. Calcium chloride. We find the chlorine. Chlorine is generally soluble, and calcium is not one of the exceptions. And so it's just going to be soluble. Anytime it's soluble, my state of matter will be aqueous. Next, I find my nitrate. Nitrates are always soluble with no exceptions. And so that one is soluble. And so it will be aqueous. For lead sulfate, I have to find sulfate. Sulfates are generally soluble, except for those containing calcium, strontium, barium, silver, and lead. So that one's going to be insoluble. Insoluble things are going to be solid. Okay, so how do we apply this to our solubility rules in our precipitation reactions? So this example problem says to write the net ionic equation for the reaction that occurs between aqueous solutions of barium chloride and potassium sulfate. So barium is in group 2. It likes to form 2+ cations, and chloride is 1-. And so barium chloride would contain 2 chlorines. And according to my solubility rules, it will be aqueous. Then I have potassium and sulfate. Potassium is in group 1, so its common ion charge is 1-, and sulfate is 2-. So a neutral ionic compound between these two would include 2 potassiums for every 1 sulfate. And then I wouldn't need the charge on the sulfate anymore, now that it's neutral. Now I know based on my double displacement reaction pattern, if I write this all out, my potassium will now bond with my chlorine, and my sulfate will bond with my barium. So my barium will be bonded to my sulfate, BaSO4, one of each. Looking at my solubility rules, I can see that sulfates are generally soluble except for those bonded to barium. So that one's a solid. And then my final product will be KCl. And that product chlorides are generally soluble, and potassium is not an exception. So that one's just going to be soluble. S does not stand for soluble though. Aqueous means soluble. S means solid. So now I can write my complete ionic equation. If you remember from an earlier video, to write things in a complete ionic equation format, we have to only write aqueous strong electrolytes as ions. Barium sulfate is not aqueous, and so that one will not be written as ions. Ionic compounds are strong electrolytes, so the remaining solutions will be written as ions since they are aqueous. So that would be barium 2+, aqueous, chloride ions, and that 2 would come out in front as a coefficient, indicating that I have 2 chloride ions. Then I will have 2 potassium ions and 1 sulfate anion. And my states of matter match what they are above. Now I have K and Cl. And so now I've written my complete ionic equation. To write my net ionic equation, I look and I cancel out any spectators. Oh, I didn't balance, did I? Always good to catch that earlier. So I caught that because I noticed that I had my potassium here, and if I only had one on this side, it wouldn't completely cancel out. And so I knew that I most likely messed up. And then I noticed in the molecular equation that that had a 2 and I hadn't put a 2 there. So that's where my problem was. But now that I got the 2 there, I can see that the potassiums cancel out and the chlorides cancel out. And so then I'm left with barium and sulfate, reacting to form barium sulfate solid. Here's a slightly different approach to the same problem. We're given these chemical formulas in names, and we're asked to find the net ionic equation. And so rather than go through the whole process of finding the molecular equation followed by the complete ionic equation, I can skip straight through to the net ionic equation if I know what I'm doing, what I'm supposed to be looking for. So I know that my first product is barium chloride, and my first reactant is barium chloride, and my second is potassium sulfate. Following my double displacement reaction pattern, I know my barium will bond to my sulfate and my potassium will bond to my chloride. That gives me my ion exchange products of barium sulfate and potassium chloride. So barium with sulfate, let's see if that's soluble or not. So according to my solubility rules, sulfates with barium are insoluble. And so that's going to be a solid. Next, I know that potassium and chloride, let's see, chlorides are soluble. And so that one's going to be aqueous. Since these starting ones are aqueous, I know that this is not going to appear in the net ionic equation. The only thing that's going to appear in the net ionic equation are barium and sulfate. So I know that my product will be BaSO4 because sulfate is SO4 2- and barium is 2+. Now I know that I need to make barium sulfate, so the only ions I need are barium and sulfate. And both of those are aqueous, and that's a solid. So you might be wondering, what if everything is aqueous? What if you apply your double displacement reaction pattern and everything is aqueous? If everything is aqueous, no reaction actually occurs. So if you pour this test tube in here and it's still clear afterwards, nothing happened. So sometimes that happens. You can still write molecular equations and net ionic equations, just write no reaction afterwards so that I know that you know that no reaction happened. But at least I can see that you know how to apply that double displacement reaction pattern. You can't write net ionic equations though because everything would cancel out, so you just write no reaction. So let's practice applying our double displacement reaction pattern and predicting the products and balancing the equation. Go ahead and pause the video and try to work this out on your own. Keep in mind ion charges. Unpause the video when you are ready to continue. All right, let's go over this. So above each substance, I'm going to write the ions that make it up. This will help me make sure that I am forming neutral ionic compounds when I make my ion exchange products. When I apply my double displacement reaction pattern, silver will bond with chlorine and potassium will bond with nitrate. That's a +1, that's a -1, so I will only need one of each to be a neutral ionic compound. Then with silver and chlorine, I will also need just one of each. Why did I put the charge? It's neutral. There's no charges anymore. All right, now I got to apply my solubility rules. Nitrates are always soluble with no exceptions, so that's aqueous. Chlorides are soluble except for with silver, and so that's a solid. And so let's see. Let's make sure it's balanced. 1 potassium, 1 potassium, 1 chloride, 1 chloride, 1 silver, 1 silver, 1 nitrate, 1 nitrate. So it's balanced. Cool. All right, now for the next one. Let's go ahead and write out the ions for each ionic compound so that we make sure that we don't ignore the ion charges. Then we apply our double displacement reaction pattern. Calcium will bond with sulfur. Sodium will bond with chlorine. That way we have our cation and anion pairs. Calcium bonded to sulfide would be a 1-to-1 ratio because that's a 2+ and that's a 2-. And then we have chlorine and sodium. And so that's NaCl. Now let's apply our solubility rules. Sulfides are generally insoluble except for those containing ammonia and calcium in group 1 and stuff. So that's aqueous. Then we have sodium chloride. Chlorides are generally soluble, and sodium's not an exception to that. So that's aqueous. And you can see that everything here is aqueous. Since it's all aqueous, no reaction happens.